Good morning, Hamilton County 4th graders. It is Wednesday. It is week 6, day 3. We are moving out of angles and we are going to build on what we learned in our angles lesson to do something a little new. So, first, if you did not write the vocabulary down at the beginning of last week, I would suggest you go back to that video and get those down before continuing with us. So we're just going to look at this for a second, and I want you to think to yourself, is it true or is it false? And then we're going to talk about it. So a point is an exact location. So is a point an exact location in space? That is true. A point is just a single dot in space, in that exact spot. It could be on a number line, it could be on a graph, it could be on anything. Now look at this figure right here. It says that this is a ray. Is this a ray? No. Why is it not a ray? Because these arrows tell us that it goes on for forever in either direction. So what would we call that? We would call that a line. Let's go to the next one. A ray goes on forever in both directions. Picture a ray. What does a ray look like? It has a point. It starts at a point and then it goes on forever in only one direction. This statement is saying it is going on forever in both directions, so that is false. What shape goes on forever in both directions? A line. So would this figure be a line? No, this is a ray because it has a starting point and then goes on forever in only one direction. A line segment has two endpoints. That is true. A line segment is a piece of our line, and so it has a starting point and an ending point. There I am. And then we have this right here. Look at this figure. Would this be a point? Yes, it would. It is like a dot, it's a circle, it's a point. A line goes on forever in only one direction? Nope. A line goes on forever in both directions. And then we have this figure right here. Is that what we would call a line segment? Yes, it is. So let's start at the beginning. Here we go. So if you have not done the vocabulary, this is a good opportunity. Or if you want to draw some examples. So we have a point, which is an exact location in space. We have a line. We know it's a line because it has arrows going from either side. We have a ray, which has a starting point but then goes on forever in one direction. And then we have a line segment that has a starting point and an ending point. Now these we haven't talked about, so you're going to have to write these ones down. So we have parallel lines. Parallel lines, or these would actually be parallel line segments, are exactly across from each other. Then we have intersecting lines or rays that intersect at a specific location. Then you have intersecting perpendicular lines. This is going to require you to remember what perpendicular was. Perpendicular is when you have intersecting points that create those 90-degree angles. You see those angles there? Alright, so name the following as a point, line, line segment, or array. What is it? It's a point. Name the following as a point, line, line segment, or array. Look at this figure. This has a starting point and an ending point. This would be a line segment. And you notice how they're naming them. So if we were going to name this figure right here, we have a starting point, and then we have this arrow over here that tells us it goes on for forever. So it would be a ray. This figure right here has two arrows going either direction forever. It is a line. And then we have another example of a ray. We'll skip some of this because I don't want to take too much time. I just wanted to show you guys. There we go. So if we were to look at these two line segments, what would we call those? Would we call those parallel, intersecting, or intersecting perpendicular? Well, in order for it to be intersecting perpendicular, it would have had to have 4 90-degree angles. If we look at these angles, we have an acute angle over here and here, and then these two angles are obtuse. So this is not an intersecting perpendicular line segment. It is just an intersecting line segment. Then we have these two line segments here. What would we call these? They're directly across from each other, so we call those parallel. This figure here, they are intersecting line segments, but let's look at the angles. Does it create 4 90-degree angles? Yes, it does. So that is intersecting perpendicular. And then we would have the parallel, intersecting perpendicular, because it creates the 4 90-degree angles. And let's make sure I didn't miss any here. There we go. It would be this one. There was only a couple of slides that I wanted to show you guys. So when we look at a map, we have a map here. These are just different streets. The question is asking us which road is parallel to Madison Avenue. So first we have to find Madison Avenue. So here's Madison Avenue right here. It's asking us which road is parallel to Madison Avenue. So we're not looking for, sorry, my ear is itchy. We're not looking for a road that intersects with our street. We're looking for one that is directly across, that is parallel. So that would be Jackson Avenue. Let's look at another map. Which road is parallel to Green Street? So Green Street is over here. We do see that it does intersect with Madison Avenue, but we're wanting parallel. So we want to look across from Green Street, which would be Cherry Street. Which road is perpendicular to Madison but is not intersecting? So which road is perpendicular, so it has a 90-degree angle in there, but it is not intersecting? Let's look. For perpendicular, we need that 90-degree angle. So where do you see that 90-degree angle happening? Right here. Let's check. It said 3rd Street. 3rd Street is right here. So why would that road be perpendicular to Madison but not intersecting? So here's Madison Avenue. If you look, 3rd Street would have made that 90-degree angle if it had continued on, but it did not intersect with it. It is just simply perpendicular. It's like it's going to go, but it hasn't gotten there and might never get there. There we go. That's all. That's the last part of it. Let's move on into our practice. All right, so we are in week 6, day 3. So we're on page 338 in our instructional book. And we're going to put what we just talked about with points, lines, rays, and angles. And we're going to see if we can't decompose this problem that these two girls are having. So Tracy tries to teach her younger sister how to draw a rectangle. Tracy tells her, draw a shape with 4 straight sides. Tracy's sister draws the shape at the right. Me. So you guys can see me. The shape includes 4 straight sides. Why is Tracy's sister's drawing not a rectangle? Well, what is the total number of sides in a rectangle? We might not be able to keep doing that. Sorry. There we go. Okay. So what is the total number of sides in a rectangle? A rectangle, if you draw it out, should have 2 short sides and 2 long sides, and they should be parallel to each other. So these 2 short sides are parallel to those, and the long sides are parallel to each other. So we have 1, 2, 3, 4 sides in a rectangle. Are the sides of a rectangle straight, curved, or some of each? Well, let's look at our drawing. A rectangle is made out of straight sides, not curved. How many corners does a rectangle have? Well, we know that a rectangle has 4 90-degree angles. So it has 4 corners. Are the corners of a rectangle like the corner of a sheet of paper, or are they narrow or wider? Well, they make this 90-degree angle right here, so they'd be more like the edge of a paper, right? Like here. So it'd be more like the lines of paper, or the corner of a paper. Corner of a sheet of paper. Do some or all of the sides of a rectangle go on forever, or do they all stop at a certain point? Are my lines going any further? No, they stop. So they all stop. Are all the sides of a rectangle the same length, or can some be different? Well, it's a rectangle, so we know that it has 2 short sides that are the same length and 2 long sides that are the same length. So could they be different lengths? There can be 2 short sides and 2 long sides, or they can all be the same, but opposite sides have to be the same length. When we were talking about the rectangle, we were talking about how these 2 lines were parallel and these 2 lines were parallel. So these lines have to be parallel in order for it to be called a rectangle. So they can be different. As long as the opposite sides are parallel. Explain how Tracy could make her directions more clear. So how could Tracy have described this shape to her in order for her to have drawn an actual rectangle? Well, she could say, draw a four-sided shape, a four-sided shape. They might not have given us enough room. With straight sides. With straight sides. That looks like an L. There it goes. Draw a four-sided shape with straight sides where it has four corners. I don't think I want to say where. I think I want to say with. With four corners, each side do they go on for each side? Do they go on forever? Nope. Each side ends. How do we want to say this? Ends when it meets the other side. Well, how else could we tell Tracy to draw this shape? So we draw four sides with straight lines with four corners. Each side ends when it meets the other side. What else is there about rectangles? What did we say about those opposite sides? The opposite sides must be what? Parallel. The opposite sides must be parallel. Alright. So this is just showing you that vocabulary one more time. Pause the video if you have not written these down. Okay? We're going to look at the reflection. It says, use geometry words and symbols to describe the rectangle below. So we're going to look at the lines first. Do these lines go on forever or do they stop? They stop. When they stop, they make what? They make corners. How many corners do you see? 1, 2, 3, 4 corners. What else do you notice about this shape? I notice that the opposite sides are parallel. And they're also congruent, meaning the opposite sides are the same length. So let's write this down using these geometry words. The shape has four sides, four corners, and four corners. The shape's opposite sides, the opposite sides are parallel. What else did we say about this shape? The opposite sides are congruent. They are the same length. They're the same length. And since the opposite sides are congruent, that means that our rectangle is made up of line segments, meaning the lines end. So the shape How do I want to say that? How did I say that? The shape is made up of 4 line segments. Alright, on to the practice. Practice page 349. Let's look at the example. Compare the triangles below. What is the same about this shape and what is different? Well, we have 2 triangles here. So they're both triangles. If they're a triangle, they have 3 sides and 3 angles. They're different. How? Excuse me, guys. I got something caught in my throat. How are they different? Well, look at triangle A. Triangle A has a 90-degree angle. It has a right angle in it. Look at triangle B. Triangle B is made up of, looks like an obtuse angle and 2 acute angles. Triangle A has 0 sides the same length. But if you look at triangle B, it has 2 sides, as the bugs come in, it has 2 sides that are the same length. Look at the shapes here. Read the descriptions in the table. Draw each shape in the column that describes it. So, looking here, all square corners and all sides the same length. So we want a shape that has all square angles, all 90-degree angles, and all sides are the same. That would be, let's look at this shape. This shape has all square corners. All of the corners are 90 degrees. But are our sides the same? Nope. So that's not going to go there. This shape here does not have any square angles or square corners, and the sides are not all the same length. So the only shape that fits that description is a square. Square corners and some sides the same length. So we have all square corners, but not all of our sides are going to be the same. So we know it can't be the triangle because the triangle does not have a square corner. So this must be the rectangle because we know that the rectangle, like the square, has 4 90-degree angles in it, or 4 square angles in it. Then we have no square corners and no sides the same length. The only shape that matches that is our oddly shaped triangle. Let's see if we can describe the sides and angles of the pentagon at the right. So how many sides does this pentagon have? We have 1, 2, 3, 4, 5. So 5 sides. 5 sides. Are all the sides the same length? I would agree that they are. All sides the same. How else can we describe the shape? What kind of angles do we see in this shape? Do we see any square angles? No, we don't really have any right angles. And it looks like we have some very wide angles that are more than 90 degrees. So this shape is made up of 5 corners, 5 corners, and 5 obtuse angles. Whoa, I totally missed my N. There it goes. Angles. Number 3. Describe how the two shapes shown are alike. Take a look at the shapes. How are they alike? Let's check the sides. How many sides does each shape have? 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5. So they both have 5 sides. They both have 5 sides. What else can we look for? Are some of our sides equal or are all of our sides equal? Well, these two sides are the same length, but these sides are not. These sides on this shape are the same length. These sides are the same length, but this is not the same length. So we could say that both shapes have some sides that are equal. They have some sides, not all. They have some sides that are the same. Wow, I ran out of room on that one. The same. And let's look lastly at our angles. Are these made up of square angles? Nope. No square angles there. They do not have any square angles. So remember, when you're describing shapes, you can also describe what they don't have that is the same. So you really have to go down that checklist. How many sides does the shape have? What do those sides look like? Are they the same size? Are they all different? Are some the same? You got to look at the corners. You got to look at the angles that make up those corners. You just got to have that mental checklist. That way you don't miss anything. So let's look down at 4, 5, and 6. We are going to draw the shape that is being described. So this is a shape fewer than 4 sides and 4 angles. So we don't have 4 sides. We have less than that. If you need a little cheat sheet, there's a key here. This has 4 sides, this has 4 sides, 4 sides, 4 sides, and then 5 sides. The only one that has less than 4 sides is a triangle. What about 4 sides and 4 angles? We probably should write that in there too. What has 4 sides and 4 angles? Well, this is going to be more than one shape. We have 4 sides here, 4 sides here, 4 sides here, and 4 sides here. So a rectangle fits that description. 4 sides, 4 angles. A square fits that description. The rhombus fits that description. And the parallelogram fits that description. And I'm going to have to look at how you spell that. Okay. Parallelogram. There we go. And then we have more than 4 sides and 4 angles. And the only shape that we have over here is a pentagon. What about all sides the same length? So all the sides are the same length. Well, we know a square is going to go in there. We know that we can't put a triangle in there because this triangle doesn't have all the same length of sides. The rectangle doesn't go because the rectangle, the only sides that are the same are the opposite sides. So we have long sides and short sides. We already said the square. Look at the rhombus. The rhombus fits that description. all of his sides are the same. And let's look at the parallelogram. Are all sides the same? Not quite, huh? It's more like a tilted rectangle. And then let's look at the pentagon. Look at these sides. These sides are all the same length as well. What about some sides that are the same length? Some of the sides are the same length. So let's look back at our triangle. It can't be our triangle because none of these lines are going to be the same. We want some. So the rectangle fits that description because the rectangle has opposite sides that are the same. The square has all sides. This is only some sides the same. Wouldn't be the rhombus. Our next one would be the parallelogram. Just sound that one out. And then we have no sides the same length, which is our oddball over here, the triangle. Number 6 has a square corner. So it doesn't have to have all the square corners. It just has to have at least a square corner. I'm not going to be able to. So looking at our triangle is going to fit that description because it does have a square angle. So we're going to say triangle. Then looking at the rectangle, we know that rectangles have 4 square angles, much like a square. What other? And then of course the square. The square has square corners, imagine that. The parallelogram, not so much, nor the rhombus. We look at these angles. These are 2 very wide angles. These are two very small angles, and acute and obtuse angles. And this looks like it is made up of a series of obtuse and acute angles as well. So we are going to say that it was the rhombus, has no square corners. The parallelogram, I can't believe how many times they're going to make us write this word. Parallelogram. Oh my goodness. And the pentagon, because the pentagon was made up of obtuse angles. Alrighty. On to our countdown. We are almost done. Almost done. So for A through D, we're going to select true or false for each statement. A, the value of 3 in 843,902 is 3,000. If this was my ones, tens, hundreds, thousands, then that would be correct. That value is 3,000. The value of the 9 in 295,917 is 900,000. Well, for one, they gave us more than one 9 to look at. But if we look, this 9 is in the hundreds column, so it's only worth 900. And then this 9 is only in the 10,000s column, so it is not worth 900,000 at all. C, the value of the 2 in 638,257 is 200. Looking at our place value, that's ones, the tens, this is the hundreds, so yes, that 2 is worth 200. The value of the 1 in 516,222. The value of that 1, let's look, we have ones, tens, hundreds, thousands, 10,000s, so it's worth more than that, so that is false. How many times larger is the value 37,000 than 37? Just like we did before, we can write this number out as if it was in a place value chart. And we can just count our place values that we have not gotten to. So 37 ends in the tens place. So we went from the tens to the hundreds or excuse me, to the to the hundreds, to the thousands, all the way to the 10,000 spot. So we moved 1, 2, 3 place values. So every time we go up a place value, we times by 10. So this is 10 times 10 is 100 times 10 is 1,000 times. Oh, you can hardly see these. Which statement correctly compares two numbers? Select all the correct statements. We have 259 is greater than 295. We can check with using place value. Our 2's are the same, so we can't compare those. But then we have two different digits in our tens place. We have a 9, which is the same as 90, and a 5, which is the same as 50. 90 is greater than 50, so our alligator should be facing that direction. So this is not going to be correct. Then we have 295 is less than 250. 59. That's not right. 259 is less than 295. Is that correct? Is $259 less than having $295? Yeah, that's true. 295 is less than 259. Nope. Or 259 is equal to 295, and that's not happening either. Alright, we're going to write 973,062 as a number. So we're going to do this as we read it. 973,000, that's telling me to put a comma, 62. I didn't hear any hundreds, so I don't have any hundreds. I have 6 tens and 2 ones. There we go. Which phrase represents 34,823? So this looks like it's breaking it down into our base 10 form, so we need to make sure we're reading this very carefully. We have 3,483. Does that sound like a real number? No. For one, it's not going to be 3,000. That 3 is worth 30,000. So the first thing I should hear is 30. Here's 34,000. Ooh, we're getting there. 803. Well, let's look back into that hundreds place. There's a number there that they didn't count, so that's not going to be right. And then we have 34,000. Sounds good. 823. There we go. Everybody was remembered. And the answer was C. Alrighty, guys. That concludes week 3. I don't know why this is backwards. Week 6, day 3. We got our countdown done. There was, trying to remember, there was something we needed to talk about really, really quick. That's right. Okay. So, as you might have known if you had read Dojo, we are going to be collecting this packet next week. Friday of next week. That's Friday, I believe the 15th or the 13th. Let me double check. That would be, where's the calendar? The 15th, Friday. So, what we need to be doing this week and next week is buttoning up as much as we can. If you're behind, you need to call me and talk to me, and we can come up with a plan to get you caught up. But we are going to have everything turned in on the 15th. That's so that should be all the way up to week 6. So everything up until the 15th, that would be, so our last lesson, let's talk about this for a second so I don't confuse anybody. Our last lesson will be page 354 will be our last page. This will be week 7 is the last week that you will be held responsible for. Okay? If you are having trouble, if you are behind, you need to talk to me if we haven't already talked about it. But yeah, we're gonna start wrapping this up. I'm sure you guys are ready, and we are ready. We are gonna wrap it up, and we're gonna get that work turned in. All right. Thank you guys. Have a happy Wednesday. Again, if you have any questions or concerns, just call me, message me. I know the next few days are going to be a little stressful, and so I'm here to support you as best as I can. Alrighty. Bye, guys.